Hello again, here's another further maths video for A-level. We're looking at chapter 2 of the Core Pure Mathematics book 1, section 2.2, where we're going to find out about the modulus and the argument of a complex number. So here's where we're going to start. I'm going to ask you to do something. Can you please consider the complex number z, which is 6 plus 2i. I want you to put that as a vector on an Argand diagram and then work out the magnitude of that vector and the angle that vector makes with the positive real axis. Pause the video, do that and restart when you're done. Okay, let's see how we get on with here. Now I've got my graph plotter up and running here, so you can have a look at it there. I've got the complex number z there, 6 plus 2i plotted here, and hopefully you recognize that what we need to do here is basically just form a little right angle triangle to find that modulus, sorry, that magnitude of the vector. So here you can see it goes 6 along and 2 up, and then the vector itself looks a bit like that, and with Pythagoras we can see that that length, that magnitude of that vector is about 6.32. As an exact surd, it's root 40. To find the angle here that it makes with the positive real axis, we're basically looking at this angle here, if you can just about see it on the graph plotter there, and in radians to 2 decimal places there, 0.32 radians. Now what you've just done there is you have found the modulus and the argument of the complex number 6 plus 2i. Here's the definitions. The modulus of a complex number is the magnitude of the vector that represented on the Argand diagram. Another way of saying that would be that it's equal to the distance from the origin that the point on our Argand diagram is. So there's our modulus, and you'll notice that it's the notation for a modulus there with those vertical lines around the z. You might have seen that before when we were dealing with moduluses in our pure maths course for regular A level. So it's kind of an extension of that idea. The argument is the angle, so that angle which the vector makes with the positive real angle is the argument, and we pretty much always write that argument in radians. So just going back to the graph plotter for a second here, we can put that on the screen here. So the graph plotter, I've got it to put the modulus and the argument there as well. And I can kind of pick up the points here. Let's see if I can do that. There we go. And if I move that point around, you'll see that we end up with, you know, a different modulus there and a different argument. And so the modulus is always the distance that the point is away from the origin, and the argument is the angle it makes with this positive real axis. Let's just kind of move it across over here so you can see how it works there. And so you can see that that's what we've got here. Okay, let's have a look at an example here where we can do this together. So say we've got the complex number there, z, which is -1 minus I times root 3. I've written it that way around just to be clear that the I is not under the root sign here. Let's just make sure that we can find the modulus and the argument of this complex number. So we'll have a look at this one together here. Right, so on my Argand diagram, I've just done a little sketch here. I want to sort of sketch where this point is. So the real part is -1. And the imaginary part is minus root 3, so I'll put that about here somewhere. So my complex number z is around about here somewhere. If I draw the line to the origin, then what I want to know is I want to know the length of that line for the modulus, and I want to know that this angle here for the argument. So going all the way around from the positive real axis in this sort of positive anti-clockwise direction here. So let's just draw ourselves to the triangle that we need. So the length of the triangle here, that length there will be 1 and that length will be root 3. And I think that means that using Pythagoras, we get the side here must have a length of 2. So the modulus of z must equal 2 here. And then we can just use some basic trigonometry to find, first of all, we'll find this angle here, and then we'll just add a half turn, which is pi radians to it. Okay. Now you might recognize this triangle, but if not, we can just do something like arctan or inverse tan of the opposite over the adjacent, which is root 3 over 1 here. And in radians, you might recognize that would be pi over 3. Oops, there we go. Can we see that here? Let me try and bring that across here a bit better. Okay, struggling here to get it in a good place. There we go. We'll go with that, shall we? All right, so the actual argument of our complex number z, therefore, is actually going to be this angle pi over 3 plus pi here. So it becomes 4 pi over 3. So it's really, really important that you actually do draw the picture here, that you do sketch an Argand diagram with a point on it so that you know exactly where your triangle sits and whether or not you need to sort of add pi or subtract it from a pi or something like that, so you know exactly what's going on. Don't just do the inverse tan or the arctan and think that's your argument, because sometimes it will be, sometimes it won't be. It all depends on where you are on the Argand diagram. Over to you then. Now it's your turn. See if you can work out the modulus and the argument of the complex number w, which is on the screen there. Okay, let's check our answer. So I've started to draw the Argand diagram, just a little sketch here. So the complex number w, I should say, w, has a real part of -7 and an imaginary part of 7. So on our Argand diagram, it's going to be up here somewhere, and this is the vector that we're interested in. So the triangle that we're going to deal with here, I think we'll look at the triangle with 7 and 7 there. So can you see what I'm doing here? I'm basically taking sort of the triangle that's here and just drawing it over here so I can see it a bit more clearly. Using Pythagoras, we can say that the magnitude of that vector there, or the modulus of the complex number, is actually going to be 7√2. And the argument of the complex number is this angle, which takes us from the positive real axis around here. Now the way I'm going to work that out is I think I'll use trigonometry to work out that angle and then subtract it from pi. So this angle here, I'm looking at inverse tan of opposite over adjacent here, so 7 over 7. So that's going to be pi over 4 in radians. So the argument of the complex number w is going to be pi minus that pi over 4, which is going to be 3 pi over 4. Okay, getting the idea? All right then, so we've met modulus and argument now, but there's a couple of other situations I just want to go over before we finish this video. I'd like you to think about the question which is on the screen here. Pause the video, have a go at it, and see if you can work out what's going on. All right, so what do you think about this one? Let me see if I can go through it here and see if you agree with what I'm about to do. So let's get the complex number z on this Argand diagram I've sketched over here on the left. So the modulus is 5, which means it must be 5 units away from the origin. The argument is minus 3 pi over 4. So what's the negative angle look like here? Well, it's going to, this way is positive, then this way is going to be negative, yeah? So you've probably seen that idea before when we've been looking at trigonometry back in our regular maths course. But minus 3 pi over 4, well, I think that's going to take us over here somewhere. So we're going to go 5 units this way, and this angle here is going to be 3 pi over 4. That's what that means. So our complex number z is going to live over here somewhere. Okay, hopefully that makes sense. Right, let's have a look at the complex number w. Now, w also has a modulus of 5, so w is also going to be 5 units away from the origin. This time the argument is 5 pi over 4. Well, 5 pi over 4, that's a positive one here. So we're going to be going round this way, and we're going to be going round 5 pi over 4. So that takes us, I believe, well, there we are, pi over 2, there we are, that's pi. So we're going to be taking sort of around about there. So we're going to be going 5 units down here. And there is our complex number w on an Argand diagram. So can you see now why these numbers are actually equal to each other? Because look, they're in exactly the same place on the complex number diagram, on the Argand diagram here. And in fact, we ended up with that because these two angles here, the -3/4, I'll write the minus in there just so you can, re-emphasize the point that we're going round in this clockwise direction here. It's basically taking us to exactly the same angle as if we'd have gone positive by 5/4 pi. So we end up with two different arguments for the same complex number here. So the point which we're coming to here really is there are actually lots of different arguments. A complex number actually has lots and lots of different arguments. All of those arguments will sort of be differ by a value of 2 pi or a whole sort of revolution apart. So if you add 2 pi to an argument or subtract 2 pi from an argument, you end up with the same complex number. So for that reason, we have an idea of what we call the principal argument. The principal argument of a complex number is just the argument which happens to lie between negative pi and positive pi. Okay, all right, hopefully that makes sense. Now, not really much more to say in this video. We've introduced ourselves to the idea of what a modulus and the argument of a complex number is. But we'll finish off by asking you to have a go at the question on the screen. So pause the video, determine the modulus and the principal argument of those complex numbers, and restart once you've got your answers. Okay, how did you get on with this one then? So you can see here I've already sketched the Argand diagram and I've put the complex number z on there already. I can see that this real part here is -9, so that has a distance of 9 here, and the imaginary part is 6, so that has a distance of 6 up here. So really I'm looking at Pythagoras -9 squared plus 6 squared. Take the square root of that and I'm going to get the modulus of my number z. Turns out that's going to be root 117, or you could have written that as 3 root 13. Okay, the argument, well, the argument is going to be this angle here. That angle is between pi and negative pi, so that's going to be the principal argument. That's what we were asked for. And the way that I think is easiest to get that one, for me at least, is to look at the triangle here, work out this angle here, and then subtract that away from pi. So the argument of z is going to be pi minus the arctan of that length there is 6, that length there is 9. So 6/9. Work out what all that becomes, and we end up with, I believe, in radians to 2 decimal places, 2.55 radians. Okay, hopefully that all made sense. Let's bring that down so we can see the whole thing, the whole picture there. All right, so let's do the same thing for the other ones then. I won't go through all of the detail here, but for your z conjugate, now that of course is -9. Bring that up so you can see it. Here we go. Z conjugate, it's -9 minus 6i. You should have ended up here with the answers. The modulus of that is also equal to 3 root 13, the same as the modulus of z. And the argument of z conjugate is actually minus 2.55 radians to 2 decimal places. Okay, so again, looking for that principal argument is going to be the one between negative pi and pi. Okay, let's just get answers for the other ones here. If we take z plus z conjugate, we actually end up with a real number. We actually end up with -18. So on our Argand diagram, -18 is going to be over here, and it's going to be 18 units away from the origin. So the modulus of z plus z star is going to be 18, and the argument, well, it's going to be going exactly a half turn away from that positive real axis, so that must mean that the argument of z plus z star is going to equal pi. Okay, finally, last one, z minus z star is going to be, turns out this one's a purely imaginary number, which is 12i. Do a quick sketch of an Argand diagram. 12i is right up here. So again, we can just see without having to do too many calculations that the distance of that from the origin, the modulus of that complex number is going to be 12, and the angle it makes with the positive real axis is going to be a quarter turn here, so the argument of z minus z star is going to be pi over 2. So the best piece of advice I can offer you whenever you're doing these kind of questions is to draw the picture, sketch an Argand diagram to make sure that you're doing the right thing here. The rest of it is just Pythagoras and it's basic trigonometry. Okay, get yourself a bit more practice by having a go at as many questions as you can from exercise 2b. We're going to be doing more work with moduluses and arguments in the next video, but until then, have fun and I'll see you next time.